Hai, Assalamualaikum. We would like to welcome our lecturer, TS Dr. Syed Najib bin Syed Salim. We are from Group 12 and today we will present our assignment project on control and instrument for the 3743 course. The team member are Muhammad Yusuf bin Muhammad Ali is me, Muhammad Syamil bin Muhammad Zamri, Muhammad Zahid bin Kamaruddin, and Nur Atika binti Muhammad. Let's get started. In this project, we are using Simulink and MATLAB to study control system. These systems are used to control and manage the behavior of device. A control system has a three-main part: sensor, controller, and actuators. Our focus is on unity feedback system, where the output is directly sent back to input. The system is simple but very effective for improved performance. The diagram here shows the input, control, and output are connected in the system. Our project has a few main goals. First, we will calculate the peak time TP, sterling time TS, and percent overshoot OS and percent for this transfer function. Next, we will simulate the system using Simulink and MATLAB and check if the system is stable. We will also calculate the steady state error is ESS for step and ramp inputs. Finally, we will compare our theoretical result with the simulation result to see how closely they match.
This is the system modeling and the theoretical derivation. Starting from the open loop transfer function with the gain k equal to 10, we form the closed loop transfer function. The resulting denominator is a third order polynomial, and solving it give one real pole at -6 and a pair of complex conjugate pole at -0.95 plus minus 1.499J. These dominant pole are then used to determine the system time response characteristic. Then next is the summary of the time response result and the stability analysis. Using the dominant poles, the natural frequency is calculated as 1.775 radian per second with a damping ratio of 0.535. From this result or this value, the peak time is 2.1 second, the setting time is 4.2 second, and the percent overshoot is around 13.7%. While for the root Hurwitz table, show all positive elements in the first column, confirm that the system is stable. Next, we move to the time response of the simulation, where the graph show that the peak time is 1.75 second, while the for settling time is 5.14. And the last one is percent of the overshoot is around 26.9%.
So here we have the comparison between simulation and theoretical results obtained. All results show similar values such as the angular frequency is 1.77, damping ratio is 0.535, and overshoot percentage is 13.7. Except peak time with simulation 1.75 but theoretical is 2.1 second, and settling time of simulation is 5.14 second but theoretical is 4.2 second. Both shows a percentage of 17% differences, which can be explained due to the practical simulation details and ideal assumption in theory. Using Hurwitz criterion to find the range of K gain, deciding the system stable or not, it is found below K value of 96.045 is stable. Equal means marginal stable, while more will result in unstable system. Shown below is the pole position of the system. The observed pole from simulation and theoretical is similar, all on the left side of S-plane, showing a type of system which is a stable system. So here we have the Simulink circuit and how we obtain its Kp, Kv and ESS value, and shown below is the graph of the system and how ESS value can be obtained by the input minus with the output, although for Kv, the ESS is infinity.
The slide shows the theoretical calculation for steady state error and error constants. From the theoretical analysis, the Kp value for the step input is 0.529, which results in a finite steady state error of 0.654. For the RAM input, the Kv value is 0, which means the system cannot follow a RAM input properly. As a result, the steady state error for the RAM input becomes infinite. This theoretical result clearly indicates that the system is unable to eliminate steady state error for RAM input, which is a key characteristic of a type 0 system. For this slide, I will explain the simulation result for steady-state error when comparing step input and RAM input. From the simulation, the position error constant Kp for the step input is 0.529, while for the RAM input is negative 0.9495. Next, the velocity error constant Kv for the step input is 1.529, and for the RAM input it is 0.05052. Based on these values, the steady-state error ESS for the step input is 0.654, which shows a finite error. However, for the RAM input, the steady-state error is 19.79, which is very large. This simulation result shows that the system can follow a step input reasonably well, but it struggles to track the RAM input accurately. In conclusion, this assignment analyzed the system using the transfer function to understand its time domain behavior. The MATLAB simulation showed that the system is stable. The steady-state error result showed a finite error for step input and infinite error for RAM input, confirming that the system is a type 0 system. The theoretical and simulation result match closely, so proving that the analysis was accurate. Therefore, this assignment achieved its objective.